Hello, it's Keith here, and this is lesson 3 of my 6502 assembly programming tutorials. Now, we've looked over the last 2 weeks at the very basics of assembly on 6502, and last week we looked at the addressing modes, which are critical to the way that we work with the 6502 processor. However, we have overlooked some very simple things, and it was just simply we didn't have time yet to cover them. And I thought it was better to start looking at some really interesting things and some very technical things before we looked at the more boring basics potentially. But now it's time to actually make sure we cover them so that we know everything that we need to when we're programming in 6502. So as well as those essentials, we're going to be looking at loops and conditions. If you're familiar with BASIC, that's the for command and the if command, and we're going to be doing that. And so we're going to learn some more commands today. They're going to be really useful, as well as some basics that we just need to know for 6502 assembly. So let's make a start. So the first thing I want to discuss with you is the org command and labels. Now, if you're using the samples I've provided with my tutorials, then of course a lot of the work will be done for you, but you do really need to know how things work. And so that's where org commands and labels come in. Now, when we use an org command, what it does is it tells the assembler what the destination of this code is going to be in memory. So if we set the org to hexadecimal 1000, then the first byte of the code will be compiled with an address of 1000. This is important for things like labels, because when we define a label, we're effectively defining a position in the code's destination memory address. So that will of course be relative to the memory address that we specify. So you can see here we've got an org statement and we're actually using a symbol. What's a symbol? Well, a symbol is a text-based label that is given a numerical value. So you can see here we're setting the org to run location, and we specified run location just above, and we're specifying it to hexadecimal 200. So what we're telling the assembler is when we install this into memory, we're going to load it into memory address 200. So everything else should be relative to that address. So this first byte would appear at memory address 200. SEA will compile to a single byte command, and what it does is it disables interrupts. This is to make our program easier to work with, because interrupts are where the operating system will do other things that we aren't aware of, and that can cause us problems. So for simplicity, we're turning them off. So SEA will turn the interrupts off, and it's a single byte command, so this byte will be at memory address 200 because we specified the org as 200 via this defined symbol run location, which we set equals to 200 here. Now you can see we've got a label here. Labels are of course defined by text that appears at the far left of the screen with no tabs separating them out. So a label is the same as a symbol effectively, but it's given a numerical value based on its position within the code. So this label here will be at position 200 because it's immediately after the org statement, but if we moved it to here, it would now be at 201. We of course don't need to know what number the label has because we use the labels in a different way. We use them as destinations for calls and jumps using JMP and JSR, and so they are automatically calculated by the assembler for us, and we just use them for their values. Now I said about symbols and labels are basically the same. They are both text-based messages that are converted by the assembler into a numerical value in the final data, but of course the symbols we define with an equals command to a specific value, whereas the labels take their value from the position in the code. Why would we want to use a symbol? Well, the reason is quite simple. I might want to have my code able to be changed very quickly without having to make changes all over the code. For example, you can see here, I've clearly had two different versions of my code, one that compiles to memory address 200 and one that compiles to memory address 1000. If I want to change the destination that I'm compiling to, I just rem this one out, unrem that one, and there we go, we've done it. And of course you can define symbols on the command line as well, so we can have a batch file that compiles to each system, and this is how I actually do my assembly. You see, I can compile my test programs to a wide variety of systems, and the way I do it is I define a symbol, in this case build A52, and I've set it to 1 on the command line, and my code is checking for that and the code is being changed accordingly. Now the important thing to understand is that when we use symbols and labels, the symbols and labels never actually appear in the destination assembled code with the text name that they have. They are converted to their numeric values. This is purely an assembler thing. So if I created a symbol with a ridiculously long name of hundreds and hundreds of characters, that has no negative effect on the size of the final code. It's all done by the assembler. So we've got the ability to use symbols and labels to give our code some meaningful text for us, but it doesn't affect the ending code in any way. So how do we use labels in practical cases? Well, let's take a look at this simple code I've written here. Very, very basic. All I'm doing is I'm showing the monitor twice to the screen. So, well, that's not very interesting, but it's good enough for a little example. So let's say we put a label here. So we've defined test label. We can put a colon at the end if we want. I tend to, but you don't need to. And then we can put a JMP. And now we're jumping to test label. So we're skipping over one of these monitors. And so now you can see we're only showing the monitor once because we're skipping over one of the monitor commands. Now labels can be used for subroutines as well. If I put my test label here and we do CLC and then ADC #2 and then RTS, this is now a subprogram. RTS means return from subroutine. Subroutine is called test label, and we are just adding 2 to the accumulator. And we can just test this now. And if we want to call a subroutine, we use JSR for subroutine. And if we run this twice and then execute, now you can see that A goes from 0 to 4 because when we run a subroutine, our command executes, and of course the monitor here is a subroutine, but as soon as its execution finishes with a return command, execution continues on the following line. So we're running test label twice, which adds 2 each time, so by the time we get to the second monitor, we've added 4. Of course, if you're familiar with BASIC, then a jump command is a go-to command and a JSR is a go-sub command. In the example we just saw, we were using the symbol with the org command, but we can use symbols with any command we want. For example, we could do an LDA from test sim here. And of course, we need to just put a hash there. And then we do test sim EQU, and we can do 66 here. And if we just compile this, you see that the 66 has been loaded in. And of course, if I change this to 67, you'll see it's changed to 67. And the point is, of course, we can use this test symbol in dozens of places. So if you want to define your screen width, you could set it to 32. And then if later you decide your screen needs to be narrower, you could change it. And in all the places you use test symbol, it would change automatically in the assembled code. I do have to point out, you do have to make sure you've got no tabbing. If you've tabbed in like I just did there, you will get an error message because it will mistake it for a command. So make sure your symbols and your labels are always at the far left hand, at least in VASM. As I said, the symbol doesn't end up in the assembled binary data as anything other than the value it contained. So if you see here, I defined a test symbol and I compiled it, and then I've looked at the listing here, which all of my exporters will output, but you can see this A5 here is the LDA command and the 69 is the value of test sim, but there's no sign of the label itself test sim in there. If you ever want to see the output, then you can have a look at these listing files, which I'm outputting for all of the computers I'm compiling for. They are quite complex, so they're not really something we're going to look at in these tutorials. Okay, so it's time to start looking at some more commands then. Now, one of the very common commands you'll see on this Z80 and a lot of other systems is increment and decrement. This is where we increase and decrease the accumulator by 1, and this is sort of common for loops and just about everything really. Now, as I've said before, the 6502 was based on the 6800 and it was a cost down version that had some features removed. And one of the features they removed was inc and dec. So we don't have those commands. So what we have to do is we have to add 1 and we have to subtract 1 for the accumulator. However, we do still have inc and dec commands for the X and Y register, which is a good reason why you may want to consider using those as your loop counters and not the accumulator. So let's have a little look at some example code here. So what we're going to do here is we're going to set hexadecimal 69 to the X register and the Y register and the A register, and we're also going to store it into the 0 page, but we'll have a look at the 0 page in just a moment. Now, then what we're going to do is we're going to show the monitor, which will show the current state of all the registers. Then we're going to use some ways of decrementing and incrementing our registers. So with X and Y, we do still have inc and dec commands, and they are incs and decs and ini and dei. So DE for decrement or IN for increment, and then X or Y for the register. Because in all cases, the commands in 6502 are just 3 characters long, so you get these kind of weird, kind of abbreviated commands. I mean, this should really be decx or decy or something, but as I say, it's de and ini and inix and dex. So there we go. But we don't have one for the accumulator. So if we need to inc or dec the accumulator, for inking we need to clear the carry and then do add carry #1. For decrementing, we need to set the carry and subtract with carry #1. Now the carry works backwards with subtract command, so if we only want to subtract 1, we actually have to set the carry first. If we cleared the carry, we would actually end up subtracting 2. A bit strange there, but that's the way it works. So let's try this out. Oh dear, I seem to have made a mistake there. I can spot what it is. I've forgotten this infinite loop here, and so my code has just run wild. So anyway, some quite amusing error graphics there. That's what it was supposed to look like. So here we go. So you can see we've got all of our registers set to hexadecimal 69 here. And then we are decreasing y. So y here has gone down to 68 with this dy command. And then we've increased x. So x has gone up from 69 to 6a. Because 10 in hexadecimal is not 1, 0, it's a. We've added 1 to the accumulator. Not an int command, but faking an int command. So that's gone to 6a as well. And then here we've done the opposite. So we've decreased x, increased y, and we've subtracted 1. So our values have all gone back to the original. So this is how we can simulate the inc and dec commands for the accumulator and how we can use the inc and dec commands on the other registers. Very good. Now, I mentioned the 0 page, and with the 6502, the thing to understand is that the 0 page is effectively kind of a fake register store. It can be used to simulate registers. And so in the same way as we can inc and dec registers, we can inc and dec the 0 page. And unlike the accumulator, we do still have the inc and dec commands. So the accumulator, ironically, is the only thing we can't directly inc and dec. So we loaded a value into 0 page address 01. And we can inc and dec that just by specifying the memory address, because notice there's no hash here. This is not an immediate value, this is a memory address here. So we're inking the memory address 01 and then we're decking this memory address 01. And we're using this memory dump here to show that range of the 0 page so that we can see that register as it changes. So let's see what happens. So the top is exactly the same as before, and here is the 0 page. So this is byte 0 and this is byte 1 here. And so you can see we loaded in a hexadecimal 69 and then we inked that memory address, so it went up to 6a again because a is 10. And then we decked that memory address and it went back down to 69. So you can see here that using the 0 page was basically exactly the same as using the accumulator or the X register. So that's the secret to the 6502. Use the 0 page as your extra registers. Now, of course, the 0 page is slower than the internal registers, but it's a lot faster than doing those kind of commands would be on the Z80. So it's really the sort of key to getting used to using the 6502. And if you're used to a system like the Z80, that's the secret. The 6502 0 page is effectively your register store, if you will, for all of your extra registers. And of course, we can use any memory address here. We can change this to inc and dec 0 page 2 instead if we want. And you can see here we've now affected this one, and this one is unaffected. And the 0 page goes from 0 to 255 or 00FF effectively. So we have 256 0 page registers. If you've got interrupt enabled though, be aware that a lot of them will be being used by your system's firmware, and that's one of the reasons we've got interrupts disabled in these tutorials. But there you go, you can see there that we've got the 0 page that we can use for our commands. So what about if we want to do a loop? Well, of course, a loop will be basically a starting number and then a decrement command, and then when a certain condition is reached, usually 0, then we will want to stop looping around. So how do we do that in 6502? Well, whenever we do additions, increments, decrements, or loading of registers, then a set of things called flags will be set. These are conditions that are met by the values in the register. And the way we detect if a register has reached 0 is using the 0 flag, which is set when the last command resulted in a 0. And so whenever we decrement a register, in this case we're decrementing x, if x has reached 0, then the 0 flag will have been set by that previous command. Now, of course, it's important to understand that it's only the last command. If we want to see if x has reached 0, then we couldn't do a DEY before the command, because then the DEY would have set the 0 flag. Now, we're using BNE, which stands for branch not equals, and the reason for that is that when we're doing comparisons with numbers, the 0 flag will be set when the two numbers don't match. Why is it called branch not equals, if not branch not 0? Well, if we're comparing two different numbers, then the difference between those two numbers will be 0 or not 0, and that's the way that the branch not equals command works. So that's why the terminology might not be entirely clear in this case of decrementing, but it makes a lot more sense when we're doing comparisons, which we will be doing very soon. So what's this example going to do? Well, we're going to set x to 3, then we're going to show the monitor, then we're going to decrement x. If x is not reached 0 yet, we're going to jump back up to this label here, and we're going to continue until we do reach 0, at which point we're going to hit this infinite loop. So let's try that out and see what happens. So you can see here, we've gone from 3 to 1, and we never show this at 0. And the reason for that is as soon as we reached 0, we dropped out to this infinite loop, because this only branched when it wasn't 0. So that's very straightforward there. So we do have a wide variety of branching commands other than branch not equals. So let's have a look at them. Now we've got BCC. This will branch if the carry is clear. Now we've looked at the carry, of course, because we had to set and clear the carry when we're doing adds and subtracts. And the reason for this is whenever you do an addition or a subtraction, if your addition or subtraction goes over the limit, so in a single byte, if you added 1 to 255, for example, that would go over the limit of a single byte number. Or if you subtracted 1 from 0, that would go under the limit of the single byte number. So the carry would be set in those cases. And so you might want to branch if the carry is set or the carry is clear, and that would be what you would do there. These are also used when we're doing comparisons in a different way, and we'll look at that in just a moment. Branch if equals will branch if the 0 flag is set. So that is effectively if the last command resulted in the 0 flag being set. We've got branch if minus and branch if plus. These are a little bit odd. Now, if you're not familiar with hexadecimal with regards to negative numbers, I'd suggest you look at one of my other tutorials which I've made in the past about how hexadecimal works. But essentially, if a normal hexadecimal number will go from 0 to 255, but if a number is considered signed, it will go from 0 to 127, and then 128 to 255 will be considered negative numbers. So it effectively goes from minus 128 to plus 127. The rather strange thing is that the value 255 is actually considered -1, and the reason for this I will just very quickly show you. So let's have a quick look at this example of what happens when we repeatedly add 1 to the X register here. Now you can see here FE is 254, and then we've gone 255, but then once we've added 1 again, we've rolled back to 0. This is because a single byte can't go over 255, and that might seem quite logical, but here's the interesting thing. So we're going to load the accumulator with the value 100, we're going to clear the carry, and then we're going to add 255. Now what's going to happen, do you think? Well, let's find out if you can guess. So what we've done is we've cleared the carry and we've added 255, but actually the value has gone down by 1. Why is that? Well, when we add 255, we are effectively rolling over from 0, and we're reaching the value 1 less than we started. So effectively 255 is -1. You see, the processor doesn't know whether 255 is a positive or negative number. I mean, that sounds silly, I know, but it all depends how you're using the registers and how you're using the numbers. And I'll just show you that again. I can actually put in -1 here, and the assembler will compile that, and you can see it worked just fine. But if I actually do LDX with -1 and compile that, you see that X is FF, which is 255. The point I'm making is -1 and 255 are literally the exact same value, and it's only how we use those values and how we interpret them that affects whether it's a positive high number or a negative low number. And that's why you have these branch if plus and branch if minus commands, because if you are treating them as signed numbers, you need those to be able to check what the registers have. And also, as well as plus and minus, we do have branch if overflow, clear and set. These aren't ones you tend to use too often, but they could be useful in some cases. So as I said, the 0 flag is set when we actually do decrements, but there are other cases it is set, and also we will want to do more advanced comparison commands. So we've learned how to use the branch command to check when the accumulator reaches 0. But what about if we want to do something with a different value other than 0, or if we don't want to use the accumulator? Well, what we can do is we can use the compare command to compare with a different number, and we can use CPX and CPY in the same way with the X and Y registers. Now it really explains why we're using the branch equals command to check if a register reaches 0. You see, the compare command effectively simulates a subtraction between the accumulator and the passed parameter, and the result will affect the flags accordingly. So if we compare a value of 3 to the accumulator when the accumulator is 3, then the difference will be 0. And this is why branch equals is effectively branch if the 0 flag is set. But if that's a little bit confusing, you don't need to worry about it, because you can see how each one of the branch commands relates to a more sort of traditional comparison that you might see in BASIC or something like that. So we're going to have a go with these now, and we're going to use the CPX command to compare the X register to a fixed value that we're going to specify. So here's the example we're going to try today. What we're going to do is we're going to set the X register to 3. We're then going to compare the X register to 2. If the X register is 2, then we're going to call the monitor. But if it's not 2, then we're going to skip over that monitor command and we're going to decrease the X register, and we're going to keep doing that until we reach 0. Now this is something quite important. We have no commands that can branch to a subroutine. So if we want to branch to a subroutine on a condition, we need to skip over the jump to subroutine command if the condition is not true. And that's what we're doing here. If X is not 2, we're skipping over the jump to subroutine command and carrying on. So let's run this now. And you can see here that the monitor was only shown when X was equals to 2. Now if we change this to a branch if equals, we have effectively run the monitor for all of the states except 2. So you can see here that we are using the compare X command here, and we are able to change what happens when X meets the condition, just depending on this branch command here. So that's just comparing to a value and branching if the 2 values match or don't match. But what about the other kinds of comparison? And so what are we going to do in this example? Well, what we're going to do is we're going to set the accumulator to 3. We're then going to compare to 4. And if A is greater than the compared value, then we're going to branch. Now, in this case, A is lower, so the branch didn't occur. But if I change A here to 4 and then compile again, you can see that we now have branched, because the branch if carry set will jump if A is greater than or equal to the value compared. But of course, if I now change the compared value to 5, we're now no longer jumping to that monitor there. So that's how we can do a compare if greater than equals. Well, what if we want to compare if something's less than? Well, we can use the branch if carry clear command instead. So this will see if the accumulator is less than the value being compared to. And you can see it of course is, because we've got an accumulator of 4 and we're comparing to 5. So what about this plus and minus commands? Well, we can branch if plus and branch if minus in the same way. So here we have set the accumulator to -1 and we branch if plus, which of course it isn't. So we don't see any monitor there. But let's just run this out and let's try branching if minus. And you can see we have indeed branched. But as I said before, values over 127 will be considered negative numbers if you use this command. So if I do a branch if minus when the accumulator is set to 255, you can see the branch has occurred. And that's because if treated as a signed number, anything over 128 will be considered a negative number. So I know that's very confusing. As I said before, if you have a look at my YouTube channel, there is a video I made about hexadecimal numbers, and it went into quite a bit of detail with a lot of examples. And you can always use the Windows calculator or even Excel with the dec to hex and the hex to dec commands within Excel to help you if you need to have more practice with that. Now, there are a few important things I do need to tell you about the branch command. The branch command is a relative command. Rather than, whereas a jump will jump to a very specific memory address specified by a label, a branch will jump a number of bytes from the current memory address, and this does come up with some limitations. For example, if I put in a test command here, ds255, this will create 255 bytes of data within the code, and if I now try and compile this, you will find it fails, and the reason it fails is that the branch destination is out of range. What does this mean? Well, a branch command can only jump -128 bytes to +127 bytes away, so it can only jump within a limited range. And if this is a problem for you, or also if you need to do a call, if you want to call a subroutine or jump further away, what you have to do is you actually have to reverse your branch. So if I want to, say, call a subroutine if the carry is set, what I have to do is branch if the carry is clear, and then I have to jump over the call to the subroutine or the jump to an address which is too far away to use a branch command, and that way I can skip over the command that's really doing the work if the condition is not the case. So that's the way we do it. And of course, the other thing is if you wanted to do else statements, then by logically, if you're branching away if the condition is true, then you're still in the current position if the condition is false. So that's the way we can do calls to subroutines, jumps to positions far away, or else statements, just by exploiting the opposite condition. One other thing I do need to explain to you about the difference between branches and jumps. A jump is a specific memory address. This means that your code has to be loaded into the same memory address that you specified with your original org command. Now, there may be times where you need to actually copy parts of your code to other memory addresses if you're doing bank switching and things that aren't the same memory address as the original. For example, your code was designed with an org statement of 200. You've now copied the code to 1000 and you want to run it. Now, in this case, you won't be able to use jump subroutine commands or jump commands because they will jump to a specific memory address that was compiled with the code in the original location. This is where the branch commands become very useful. But what about if you want to branch always, have no condition at all and always jump to a specific location? Well, in this case, we would need the branch command, BRA. But only the 65CO2 has it. Unfortunately, R6502 doesn't have that branch command, but we can simulate it. What we can do is we can clear the overflow flag and then branch if the overflow is cleared. This will in effect always branch, and this means we can do a relative jump to another memory location in all cases, and I'll just show you that now. Now, of course, this has branched out and this has no real benefit to us in this case, but this piece of code here would be relocatable because it doesn't matter where this would be executed. Because this is a relative branch, this is always going to be the same jump in all cases. So if you need to do relocatable code, using branch commands is really a necessity. Now, of course, that's going to be quite confusing and you probably won't understand that at this stage, so don't worry about it, but just bear it in mind in the future if you ever need relocatable code. So we've learned we can use the compare command and branches to do if then kind of statements, and of course if we've not branched then we've effectively got an else statement. But what about more complex structures? Now, the important thing to remember about assembly is that any other programming language compiles down to assembly. So if you're used to C++, any structure within C++ can be made in assembly. It's probably just going to take a few more commands and a little bit more time. So now I want to demonstrate this by showing you how we can do a case statement via lots and lots of different compare and branch commands. So what we're doing here is we're loading in x with 4, we're decreasing x in this loop, and then depending on the value in x, we're comparing and branching out to these case statements where we're showing letters. Pretty straightforward, and let's execute it here. So the result isn't very interesting really. You can see we've just shown CBA because the first time x was 3, so we branched out here. The second time it was 2, so we branched here. And then it was 1, we branched here. And of course, when we were finished, we just ended up on this infinite loop here. But the point I'm making is by combining multiple compares and branches, we can do much more complex structures. And as I've said, this is what the C++ you may be used to will actually compile down to when the assembler runs it. The point is that anything C can do, assembly can do, and assembly will be as fast or faster if you can do it as well as the C compiler did. Because, as I say, assembly is the bottom of the chain when it comes to programming. Anyway, that's all I wanted to cover today. It's been quite a long lesson and we've covered quite a lot of things. I hope you've enjoyed it. We're going to be continuing next time with some more commands, so please follow me for that. Anyway, thanks for watching today and goodbye.